Welcome everyone to this webinar dedicated to the snow and ice products, which are delivered by the Copernicus Land Monitoring Service. So those products are produced or generated over Europe, and they are implemented under the delegation of the European Environment Agency. So we have Joanna Prestowska and Lorenzo Solari from the EEA to share this presentation with me. My name is Florence Marty and I'm working at Magellan in France. We also have Chamal Melitanic that is connected and is from the Finnish Meteorological Institute. So the objective today is to get you familiar with the products by in introducing you the different way to access them. So I will share the presentation with those three co-chairs, and here is the agenda for the meeting. So it will last about 1 hour. First, we will give you a summary of the snow and ice products at high resolution, which are based on Sentinel-1 and Sentinel-2. We will also have a specific section to present you the different way to visualize, search, and download the products. We will then present two demos showcasing two different products. The first one is the aggregated ice product. So this is a particular product because it is actually a database that has a dedicated data access. And in another demo, Chamal will present how you can manipulate the daily snow cover product called GFSC. And then we will have a question and answer moment, a session, and also in the meantime, you can answer the survey on Slido. So I will give the floor to Joanna for this introduction of the products.
Hello everyone, I am Joanna Prestowska from the EEA. Here is also my colleague, Lorenzo Solari. And today I would like to present you with our pan-European high-resolution snow and ice monitoring product. So what does the product describe? The product describes snow properties on land and ice occurrences on the hydrographic networks. This part of observation is part of a larger whole, the cryosphere observation. And most of our snow and ice data is disseminated in the near real-time NRT, which means that the data is available within 6 to 12 hours of satellite observation. And here on this slide, you can see two of our products. On the left, there is a fractional snow cover product. You can see the figure with pixels. Black means 0% snow cover, and white is 100% snow cover. It's from January 2021 from Madrid, Spain. So you can see how it has been changing through January when the snow has fallen and we have many white pixels, and then snow has melted and there are many black pixels. And on the right, there is an example of our aggregated river and lake ice extent product. You can see here the ice extent on Vistula River in Poland and on the nearby lakes. Next slide, please. Okay. And here on the top left picture, this is our area of interest. The data set is generated over the entire EEA 38 plus UK. And what are the use cases? Snow and ice can be used for a wide range of applications. For instance, in the field of meteorology and climate, hydrology and water management. Snow and ice parameters are critical. That's why we need them in near real-time observations. because they can help us to assess natural hazards, for instance, avalanches, floods, detecting river ice jams. The data can be also used in winter tourism, agriculture, forestry, in research. Here you have two use cases. On the left bottom, you can see an image from the Pyrenees from September 2020. This is the fractional snow cover image. So that year, snow has been detected very early in September already. Near real-time observation allowed for a quick response. Some trails and roads were closed, maybe some lives were saved. On the right, you have two images from the Oder River in Poland. This is showing the river ice detection. And on the bottom one, you have action of icebreakers on the Oder River. Next slide, please. Now I would like to quickly introduce you to our product portfolio. So we have three types of information. There is snow cover extent, there are snow conditions, and ice presence on the lakes and rivers. So there are 5 snow products. 2 are snow cover products. We have the fractional snow covers already mentioned that provides us with snow fraction on the top of canopy and on the ground. Then we have daily cumulative gap filled FSC that completes the fractional snow cover product. We have 2 snow state conditions products, wet dry snow product that differentiates the snow state condition between wet and dry. And then there is SAR wet snow product that provides information on the wet snow extent in the high mountains areas. There is also persistent snow area product that is produced on a yearly basis and provides the extent of a persistent snow cover. So snow cover that is present throughout the whole year. And then we have 2 ice products defined on the hydrographic networks. There is river and lake ice extent that provides information about ice cover, and aggregated river and lake ice extent that provides information about the ice extent. The data is available since September 2016. And next slide, please. Today we will focus on 2 of our products, daily cumulative gap filled snow cover. As I mentioned, this one completes the FSC product, and it's worth to mention that it's gap filled both at spatial and temporal scales. This is the raster product at 60-meter resolution, provided in near real time at each release of fractional snow cover with dry snow product or SAR wet snow. And is provided in WGS 84 projection. The demo on this product is coming afterwards. And the next slide, please. The second product that we'll focus on today is our aggregated river and lake ice extent. This one provides the % coverage of snow covered or snow-free ice on lakes and on 10-kilometer river sections. It is specially aggregated product and available in 2 versions depending on the data source. And we have this product provided in PostGIS database format in LAEA projection. It is updated every day. And there is also a demo coming soon on this product. And with this, I would like to give the floor back to Florence. Thank you.
Thanks, Joanna, for this short introduction of the products. So I guess you have questions on the products, and hopefully we will answer part of them during the demos. For now, I will present you the different ways to visualize, search, and download the products. I have this slide to highlight that the main information to keep in mind, to take away, is that the main access is the Copernicus Land portal. So the Copernicus Land portal has a dedicated page regarding the snow and ice products. So I can open it, and we will see together what are the different tabs. Sorry. So here I am on this Copernicus Land Monitoring Service web portal. I've selected the pan-European products because the snow and ice products we are talking about are only delivered at pan-European scale, and they are delivered at high resolution. And on this web page, you will see that there are different tabs, one for snow products, the other for the ice products, and you will be able to find the technical documentation related to the products. So I mean, the description of the product content, also the description of the algorithm. There is a data access tab here where you will find the main information to find the data. And then there is this important tab, user section, where you can access the previous webinars, because this is the third one we organized today. And we also already discussed about particular data access, for instance, the use of the WMS fluxes. So I'm coming back to the slides, and here is a slide that summarizes the different access. So the first one, the main one, is the Wikio interface. So Wikio, probably you've heard about this. This is a DIAS, a data access, data and information access services. And this DIAS is not only an interface to access the products, but it also provides some computational resources. And this is on which the production relied every day. Every day we open virtual machines, etc. So this Wikio portal is providing a single access to all Copernicus products, and we are going to develop it just after. We have also a dedicated portal called Cryo Portal, on which you can only find the snow and ice products we are talking about. We have web map services, so some fluxes you can integrate in your maps, in your different softwares. And there is the RLAE, so the products Joanna just mentioned, the aggregated river, lake, ice extent product. So this is a database, so it has a dedicated data access. So I will start with the description of the Wikio interface. So in this interface, you can visualize the products and search for products. And if you wish to download, you will have to register. So to create an account, all products are free, and registering to Wikio is also free. So here I'm going to show you how we can visualize the products on the Wikio interface. So you have this wikio.eu webpage, and you can find the data catalog. So by default, there are two layers which are displayed, and you can remove them by using the cross and add some layers that you would like to see. So here we are going to look for snow and ice products. So in total, in the Wikio catalog, you can see there are products derived from different Sentinel constellations, focusing on different domains, for instance, burnt areas. Here I'm going to look for products about cryosphere and delivered by the Copernicus Land Monitoring Service. I can see there are 8 different data sets. They correspond to the product Joanna introduced just previously. And I'm going to look for one specific. Let's focus on the fractional snow cover. So this raster at 20-meter resolution based on Sentinel-2 optical imagery. So I can see the details, an abstract describing this product. And I can add on the map the different layers. I will select one or the other. In this case, I will select the snow cover fraction on top of canopy, the one I can see from the sky. So you can see there is a little banner in red indicating that you have to zoom in on Europe at European scale if you would like to visualize the product. So here I'm going to zoom on the Alps. I can see a Sentinel-2 swath, and I can choose also at the bottom. I can choose the date I want to display. So here we are in March 2022, and I can, if I like, display another product in the background, etc. So this was to introduce you to the Wikio viewer. And actually, we can also use this portal to search for data and download them. So here, I will define my area of interest. I already loaded the fractional snow cover layer. You can see here on the top left. And I'm going to select the button download. But beforehand, I have to check that I'm already signed in. So I created an account, I logged in, and I'm going to download products on a specific area. So I copy the area of interest from the map. I can define on which date range I want to look for products. So here I will choose November 2021. And I'm going to play with some parameters. For instance, here I define that I want a cloud cover, the minimum cloud cover percentage should be 30% of the image. So I can see on the job tab that the results are loading, and I can download them, the products individually. And it will result in a zip file that you will have directly on your working directory. So this is how you can do if you'd like to download a few data punctually, for instance. But there is also another way to download data in a more automatic way and more efficient way from machine to machine using an API, the API of Wikio. And this API is called Harmonized Data Access, HDA. So Jamal will make will go in further details on this API. So now I'll have a word on the WMS, the Web Map Services fluxes that you can integrate. For instance, in your application, web applications, in your QGIS, for instance, if you are familiar with those geographical information system. And just to mention that Wikio is doing the same. They rely on this WMS server. And so for each product, we have a WMS flux that you can add to your QGIS. And in the previous webinar, actually the first webinar, we dedicated a large moment to explain you how to visualize the WMS layers in QGIS. If you're interested in, you can, those slides will be shared. You will find the link to this tutorial. So then we have this dedicated cryo interface. I also call it the Finder. This interface requires a dedicated registration, different from the Wikio one, if you want to download the products. And here, so I'm going to log in, to go on the Finder. This is how it looks. So this is a quite intuitive interface. Here on the left, you have different parameters you can fill in to characterize your request. So we can find the observed date range. We also have you can search for specific location or specific Sentinel-2 tiles. And here, for instance, within the Snow and Ice catalog, I'm going to look for a GFSC product. And I'm going to define with this tool an area located on the Alps. I place search. And for instance, I will show this product here. So I can select it from the screen, and I have access to all the characteristics of the product. So here I have the name with the date. So this is a product that has been generated yesterday on 12th of April. This is a GFSC product, so it means that it's a combination between Sentinel-2 and Sentinel-1 observations. I can see the different layers within the zip file that you will be able to download. And also what is interesting is that I can see the footprint of the Sentinel-2 tile. I can also click on this thumbnail and have a possibility to have a quick look of the product to make sure that this is something I'm interested in. So if you like to download the products, you will need here to register first. And in the same way that in the Wikio portal, you can use an API to perform some automatic and efficient requests, you can also rely on the CRYO API. And this API, you can rely on a Python script that describes easily how to use it. There is also a tutorial that has been presented in the first webinar if you'd like more details on how to use this API. So here let's go back to my summary slide. Today, we are going to focus on how to use the HDA API and also the RLI database just after. So maybe Lorenzo, I can give you the floor to introduce the different demos. Thanks.
Yes. Thank you, Florence, for explaining how to assess the snow and ice data. And so I think that now we will move to the more practical and also exciting part of the webinar, where you're going to see the two demos that will demonstrate how to manipulate the aggregated ice product, so RLI, and the daily snow cover product, so GFSC. And the demos will last around 20 minutes each, and will be based on Jupyter Notebooks. So Jupyter Notebooks are a great way to explore and work with the snow and ice product. And the notebooks can be assessed in many ways. So one is through the Wikio Jupyter Lab environment. And to assess this, you should register to Wikio and follow the instruction you will find at this link that you can find in the presentation. And or you can assess the notebooks from Wikio for Land GitHub and run them on Visual Studio Code or any other compatible environment. So that's it for my introduction, and I give you to Florence back the floor for the first of the two demos. Thank you.
Yes, so we're going to start with the ICE product. So I hope everyone can see the screen well and hear as well also. So we will travel a little bit, and we'll go to Poland with this demo. In the northern part of Poland, there is a region called Mazury, and this is quite famous, quite touristy, because there is a lot of lakes in this region. And I think this is a protected area, so this is why there is a biodiversity and some visitors. In this area, we have the Schnoardwe Lake. I hope my pronunciation is not too bad. And the Roche Lake we are going to focus on today. And the Schnoardwe Lake is actually the largest lake in Poland. And this is common to navigate on it. So on this picture, you can see this is a screenshot from the Wikio portal, the Wikio viewer I've just presented before. So here I displayed in the background the Sentinel-2 observation and also the river and lake ice sextant product. So we can see that the region is totally snow covered or ice covered, and the river and lake ice sextant highlight the different lakes that are very numerous in this area. So this product has been generated after an acquisition in January 2021. And we remind that the river and lake ice sextant, and in particular the aggregated ice product, is available on the different lakes and different river segments of 10 kilometers long on the EURhydro database. So some of you might be familiar with this database because this is a product that is delivered by the Copernicus Monitoring Land Service. And on the right, we have an example of a river section in yellow. So this river section is along the Vistula River, actually. And this is part of the Vistula River Basin, and there are approximately 30 watersheds in the EURhydro network. So on the bottom table, you can see that this section is characterized by the river kilometer. So it means that here we are located approximately at 400 kilometers from the Vistula mouth, located in the Baltic Sea. So we are going to see how the aggregated river and lake ice sextant product enabled us to detect some ice events, ice occurrences in this Polish region. And in particular, what are the benefits of this product? This is the fact that this product is light and is not required to manipulate some raster data. This might be easier for some of you who are not very familiar with those heavy files. And so now I'm going to move to the Jupyter Jupyter notebook here. So I followed the instructions given by Lorenzo. I connected on the Jupyter Hub by Wikio. Here on the left, I can see my Jupyter notebook called Demo RLI Poland. And we are going to start with an introduction, reminding that all we are talking about, the product content, the algorithm, they are described in a product user manual that you can find on the Copernicus Land Monitoring Service page. And what is particular with this product, compared to the other snow and ice product, is that the data are stored within a database that is always accessible and accessible through a specific API. So to use this interface, you do not require to log in or to register, and this is quite different with the other product. So the RLIE product is made actually of two tables. The first table stores the statistics, the ice cover statistics. Another one is storing the geometries, I mean the contours of the lakes and the river segments that you want to study. So there are two distinct procedures called remote procedure calls, RPC, and you can use them. The first one here, you can use it to retrieve the statistics data. You can use the second one to retrieve the geometry. So the fact that we have two different RPCs allows to download the geometry layers, the vector data, only once and not systematically. So it's much more efficient once you have already downloaded the geometry once. So here there is an example of a request. So you can see on your browser page that there are many numbers. So I will not go into the details, but here we can see a date. Here this is time, and there are snow cover. There are statistics, and actually this is not easy to read in such way. And I'm going to focus on the URL at the top, so you can see get RLIE with the different parameters. The first one is called geometry WKT, but we have also a parameter on the cloud coverage and also start date, completion date. They are going to define the date range of your of interest. So this way to build the URL manually to visualize the data, this is not friendly at all. So here is why we developed a Python script that facilitate the use of this API. So for the rest of this demo, we are going to rely on this Python script. So here is the link. The script is hosted on the Environment Agency, European Environment Agency GitHub, and you can see it here. And you can download it here as a zip file. So when you are sure that the Python script is uploaded in your working directory here, we can go on. So we'll start by loading some modules in Python. So the main packages that will be used in this demo are pandas. And pandas is a common library to manipulate data in the form of arrays. We have also matplotlib, pyplot, quite common for visualization of the data. So we are going to load the different packages. And then I'm going to define my area of interest. So I'm focusing here on this the Mazory region in Poland. So by using the Wikio, the Cryo Finder I presented before, I can simply use the polygon tool to draw my area of interest. So it could be bigger, larger, cross countries, etc. There is not issue. Then, when I click on search, as I did before, I will get a list of results. But here, this is not what I'm interested in. I will not focus on this list of results, but on the URL here. Sorry. And actually, this URL is quite similar to the previous one. It contains different information, and it's characterized my request. So it means that here I can find the geometry, the definition of my geometry. Above, I draw 4 points. One is here, the second one, the third, the fourth, and the last one is identical to the first one to close the polygon. So this is this geometric definition that I'm going to use further to download the ICE statistics. So note that this way to write the geometry is very similar to WKT format, so well-known tests. This is a format that is commonly used to define geometry in cartography, and this is there are just some adjustments to do on the format. So now I'm going to download the statistics. So I need to import the CLMS downloader for RLI products. So below here, I copied the geometry from the Finder URL. And I mentioned that this geometry is called geometry WKT here. I will also define the name of the folder where I would like to find the results, the outcome of the command. Here I can also define the range of the dates. So as Joanna mentioned, the Snow and Ice products are available from September 2016. Here I've chosen to look for ice statistic from December 2017 to 2022. I also decide to not to filter the data. If there are cloud coverage, for instance, I will keep all the data. I also confirm that I want to request the geometries. So it means that it will call the two different RPC commands, the one to download the data, the RLI statistics, but also the one to call the geometries. I specify that I want the output to be in the form of a CSV file, but also a variable that I could manipulate in Python. So I execute this cell, and then I'm going to apply the command download RLI products with the different parameters I've defined above. So here there's a red message because actually there are already some things in my output folder, but this is not an issue. So I can see the output of the command. It's requesting the geometry first, according this command here, this URL. It has written the geometries in the CSV file. And then it's doing the same to retrieve the data for ice statistic. And he found about 80,000 products, RLI products. So if I go to my output folder, I will see that indeed I have the RLI CSV, the geometry CSV files, but also metadata together with all this data. So now I'm going to manipulate those CSV files with Python. And first, I'm going to open the ice statistics, so the rli.csv file. And I'm defining a command first to make sure that the data is well formatted. And I'm going to sort the RLI value by date-time order with ascending order. So in this table, I can see the content of the statistic table with the date-time column, the different percentages describing the conditions on the water body. There is also a QC layer I will come back on, and the source. So here it means that we used Sentinel-1 and Sentinel-2 combined to deliver the ice statistics and the other statistics So the QC layer is also a result of the different level of quality of ice retrieval from Sentinel-1 and Sentinel-2 products. I have the river kilometer ID also here. So this is an ID associated to my geometry. It could be a lake or a river segment. Then I'm going to open the geometries, and here I'm going to use a quick command with pandas that allows to sort the data by area and to only keep the two largest lake of the area. So on this table, I can see the different characteristics. River kilometer here is set to 0 because this is a lake. We're not talking about a position of a segment on the river flow. This is included in the Vistula River watershed, and there is an ID associated to this Snoardy Lake. And this ID is actually the ID that refers to the river kilometer ID of the RLI table here. So in the next command, what I'm going to do is to make a plot. And first I'm going to isolate the statistics regarding only those two largest lakes, Snoardy and Ross Lake. On this line here, I will I'm going to sort the data and only keep data with a quality confidence, the best one, so 0. And then I'm going to plot the data, but first I need to execute this one. I'm plotting this data here. So you can see in orange the Snoardy Lake, the smaller one, in blue the Ross Lake, and you can see over the period of study that the data agrees well together. In particular, we can observe some interannual variations. In 2020, for instance, the winter was not so strong. Apparently, freezing up was not very intense. But in 2021, we observed that the ice percentage on those two lakes was pretty high. So this was a way to manipulate the data with Python, but please be aware that we can do something similar using QGIS. So here I go back to the CSV file, and I used a tutorial that you will also find as a material of this webinar to load the two layers, the geometry CSV and the RLI CSV, the two layers within QGIS. So here are my geometries, the different lakes, according my area of interest. And below, I also plot the statistics table. So in QGIS, you can use the SQL command to make some filter, to filter the database, etc., to look for specific data. So here I will open the database manager, select the layers I'm studying, and will apply a SQL command. So SQL is a language to manipulate the database, to add data within, to remove data, to sort, etc. And here we apply a command indicating that as an output, we would like to have the ID, object name, and area of the geometries, but we would like that they are ordered by descending area. So it means that when we execute the command with F5, we have this result here, the Snoardy Lake on top, the Ross Lake just after. And then we can apply another SQL command. So this is made on 3 different lines, but actually it's a single one command. With this command, I'm going to make the link between the Snoardy Lake with this ID here, and to only plot the RLI statistic, the ice percentage on this the Snoardy Lake over the time period I'd like. So then you can, if you like, download this the outcome of this request in a new layer that you can manipulate further within QGIS. So I'm going to conclude with this aggregated ice products. You can identify ice occurrences on rivers and lakes, and then once you have done this, you can go further and focus on a specific native product, the river and lake ice extent product. And there are many applications for these products, navigations, but also biodiversity study, climate change study, etc. So I'm going to end and give the floor to Chamal. Thank you.
Thank you very much, Florence. We are a bit late on the schedule, so I will try to be a bit faster, but as it is mentioned in the chat, the recording will be provided. So if you don't have time to stay after 1 o'clock, you can just go for them after they are published. Can you share back the presentation again? We can show the first slides there. And then we can switch to Jupyter Notebook.
Yes, I closed it quite fast. In the meantime, you can ask your questions in the chat. I think Joanna and Lorenzo are partly answering them also. Please, Chamal.
Yeah. So the GFSC product. So because there was a question in the chat also, I will go a bit into detail here. What is the GFSC product? Basically, like Joanna presented before, it's a gap-filled fractional snow cover product. But how we do is that, so in the portfolio, we already have the fractional snow cover from Sentinel-2. And then there's also wet snow products from Sentinel-1. The resolutions of those are different. FSC is 20 meters, and the wet snow products are 60 meters resolution. So how we combine this together is, first, we do a special gap filling. So we do it in the space domain by merging FSC and wet snow products in the same day. But because of the resolution difference, as it was asked, we resample the FSC into 60 meters. How this is done in detail is provided in the ATBD, and the user manuals are already linked in the chat, and ATBD links should be also there, and it's quite easy to find. And then after the space domain, we have a gap filled one for that day, but we also go back to 7 days past and use that special gap filled ones together to create a more complete one. So inside GFSC, there is up to 7 days of data, and the number of products that are used can change between even 1, 2 to 10 products or 14 products, maybe, if there are many products during the day. One property of this product is that so FSC from Sentinel-2 is coming every few days, and then also the from the Sentinel-1, but they are on different days. So what we are doing is we are using a combination method. So we produce a GFSC whenever there is new data. So we don't wait for them to overlap. But then during the day, there is new products for, let's say, a few hundred tiles, but then for other tiles, there is no new data. So in that case, during the nighttime, we still produce a product for that day using the products that are already available. So ideally, there is a product for every tile every day for GFSC. But it is also possible that there might not be new data for last 7 days, and this is happening for some tiles, especially on the edges of the coverage, and this depends on the cloud cover also. So there might not be always one, but there is generally one. Yeah, so in the demo, we will do 4 things. First, we will access the Vekeo database using the HDA API in Python. We will download some products, and we will read and visualize them quickly. Then we will manipulate the GFSC product. What we mean here is that, like I said, it's a combination of many products. So there is an option we can do. We can select the data according to the age of the pixels and also according to the sensor type. So when we have a layer of GFSC, it's not just only the FSC layer, but there's also some auxiliary layers that shows how old is each pixel. And there's also QC flex, and in one bit of that, there is information showing that where is that data coming from? Is it coming from a Sentinel-1 product, or is it coming from a Sentinel-2 product? Now here we can switch to the Jupyter notebook. Hopefully there won't be a technical problem. These live ones are a bit risky. Okay. Now, since the presentation is changed to mine, you might need to go over that and pin it to the middle. If it's not shown, you can see the tips in the chat for that. So Vekeo EU, it also has the Jupyter Hub, where you can run Jupyter notebooks using already defined Python environments with required libraries, the ones that are commonly used. For that, you need an account, and you can have one if you don't have, clicking from a register, and it's quite a straightforward dialog, and you just submit it, and you can have it during the same day. I think it takes maybe 1 hour or something. Then we can sign into Vekeo. Now we are signed in. So Florence has already shown the Data Explorer. But what we will use is the Jupyter Hub, and you can open it from this icon. It takes a bit of time to open, but not so much. Okay, because I was logged in before, it didn't show the starting screen, but what you will have, there will be a starting screen, and you will choose how to start a virtual machine. It's just a 2-click straightforward dialog. And there are also steps in the slides that we have shown, and you already have gotten one with an email before the webinar. There's also like step-by-step instructions how to come to that point. All right, so this Jupyter notebook is already uploaded to Vekeo GitHub repository. So you don't need to go to a website or anywhere to download it. What you will do is you can download it directly from GitHub, and this step is already also provided in the slides. When we just use that command in the main folder, it will clone the repository to us. 1 second, and that's already there. Now it has come to our Explorer here. If it doesn't show directly, you may need to use the refresh button. And then we can go, this one. We can go to our folder. So this repository also includes other examples. Our example is inside Snow and Ice folder, and it's that one. And during the notebook, I will not try to go like line by line in detail, but going up, I will keep a high level here. So there's introduction, which I already presented. First, we import our required libraries, and there isn't actually a special one here. GDAL, NumPy, Matplotlib, what we will use, and other libraries that we use to read folders and files and so on. So there is one small issue here. It's that the HDI API Python library is not available by default in this kernel. So for those who doesn't know what a kernel is, basically when you click here, you can choose which environment to use. There are some already provided in Wekio or Jupyter Hub. The default one is at the moment Python 3, but then there's also Mini Wekio Lab, and this will be the default one in the future. So you may need to change it back if you work on this later to Python 3, which I have prepared this notebook on, so it will be the safe option. So I just made an exception here so that if the HDI library is not available, the script will install it. And this is also valid for XML to Dict library, which is a library to read XML files. Same script. So let's go over this. Import it. Also that one. So now they are imported. First, how do we access the GFSC products through HDI library? Now, how to use HDI client, the Python library? There's more detailed notebooks and documentation in Wekio and Wekio GitHub, which the links are provided here. And I will only use the ones that we will need, the commands. It's pretty simple. The first thing is the authentication. It is also explained more in detail in the documentation, but we will use that method which the HDI library can read your home directory, and it will take the credentials from there. The credentials are stored in that file, hdi.hdr.arg. So I included also a small script here that if you don't have this file, if you didn't enter it before, it can create one using your username and password. Now, the username and password here are the same ones that you logged into Wekio. There is no separate account. So when you change your username and password here, it will make one. But since I already have one, this will just skip it. Credential file already exists. Now we can start the client. We just use that line. Now it's loaded. It read the authentication information from there and used the default configuration. So how do we search the products? We use a dictionary, a JSON object, and we give it to the HDI client, and it finds us the products. Here is an example. There's different keys which can be used to search products. And this is again explained in the documentation in more detail. The options that one would use in common, that would be like a bounding box, the extent, the date range, the product identifier where you can search it, the name of the products, etc. One nice feature is that like Florence have already shown how to use the Wekio.Explorer, and when you go there, you can download the products from there. When you are in that screen, maybe that's a bit too small. Let's make this bigger. When you are searching the products there is a button after you make the search, this icon. And when you click it, you can show the API request. So if you have a more complicated request, so to speak, a custom one, you can go there and you can copy paste it as a dictionary and use it in the search. Like this. But in this example, we will go a bit simpler and we will use one product from one tile. So how we can do is that we can create a dictionary ourselves using that fields for this tile and that date. It of course uses a strict format. So we first change our date to this format here, and we use the tile inside the product identifier because there is no separate option to search a tile. What's the tile? But the tile name is in the product title, product identifier. So when you enter it there, it searches as a part of it. Now we can create this object, and now we will search it using the HTA. Another trick here is that HTA client has a configuration. It's a time sleep and timeout, so that if there's a problem in the search, a connection or account problem or anything, normally by default it waits for an answer from the database 200 seconds, I think, which is quite long. If you have a problem, you won't see it immediately. So let's change it to 10 seconds here in case we have a problem. Generally, it's working quite well. By problem, I mean I don't think it will be from the server side. But what I have seen, which has occurred here, is that, for example, if you leave your Jupyter Hub open and go have a break and you come back, there might be a timeout that your account is closed or something like that. Then there might be an authentication problem. But when you log out and log in again, restart the kernel, it comes back. This takes a few seconds. Yeah, now it has worked. I have also included here a cell that in case the search didn't work and there is already products in the products folder, they can be used. But in that example, we don't need that. It has worked. Now this client has returned us an object, the matches, right? Now we can parse that response into a custom one so that we can use it more compactly. Again, the details of this object is available in the documentation, although it might require a bit of playing with it to see the parameters and such. But what we will do here, we will read it line by line, and we will make a list of dictionaries in that format so that we can get the title of our product that is found, the tile, the day, the curation time, and the directory that we will store it in. The curation time here is a property of GFSC product. And it is the time that when the product was being created, the time that we searched the HRSI database for the available products. And so that means that at that time, the product used all the available inputs of fractional snow cover and wet snow products that has in the database. Now, why is it in the product? Why do we use that? Is that there might be multiple production during the day for GFSC. For example, let's say there's a product in the morning. It has come, it has arrived, and we have created a GFSC. Now in the afternoon, we have another wet snow product, and we are in real time updating this. There is no acoustic signal anymore. You mean you cannot hear me? Does anybody else can hear me?
I think it might be on the user side because we can hear you.
You can hear.
Yes.
Yeah.
Okay. I think, Tom, you have a problem. Sorry for that. I hope you can solve it.
At least it will be recorded on the video, so it will be accessible.
Yeah.
So we can continue.
Yeah, creation time. So so that we can separate these products during the same day. There can be 2 products for that tile or more. Then there's the creation time also in the file name so that you can see what is the latest one. So here we parse that information, and in the search there's 1 product found. So there was only 1 for that tile and that date. And we listed, so the day was the 14th of March, 2020. And it is for tile T32 VMN, and the creation time was 6 p.m. Which is at the end of the day, which should cover the products that are arrived during the day. So let's download the products to the products directory that was defined in the beginning of the script, beginning of the notebook. And one thing to note here is that these products are downloaded as zip files, then you need to extract them. So there's this cell to do that. Wait, already in the product directory. Let's see what did we define, because this shouldn't be in the directory. I don't see it. I think because we used, yeah, because I have used this on a different folder. It is using an old one. Let's just fix that. Okay, perfect. Because yeah, I have tested that before in a different folder, so it was using that folder. Now it has updated and it has downloaded that product. The things that we should talk about here is that where you might have a challenge, so to speak, is that the zip files that is downloaded by the client are, they don't have the extension zip. So when they come to the same folder with the product one, and when you extract them, there might be a conflict in Linux. So what we do here is that rename those files with a zip extension, then extract them so that it will be safe to download. Now we have it in the products folder. We can see here, right? There's a few files for TIFF layers and for TIFF layers, and there's also one XML file which has the metadata. Now we can go reading and visualizing the products. Now we define here some functions. First one is how to read a TIFF file, and it reads the data and also the color map that we will use, which is already integrated in the raster. This is not valid for all the rasters, but it is valid for the QC layer and the FSC, GFSC layer, which is named, well, it is GF layer in that product. For two others, there is no color map. We have that here. Then we have another function that reads the product files, and it uses the reading the TIFF function to read all these 4 layers and also the XML one. Now here we use the XML to dict library. Then we have another function to make this put it compactly in one dictionary, which is in this format. Right? We have everything we need. We have GF, the color map of it, QC, the color map, QC flags layer, AT layer, which is the acquisition time. Then there's metadata and the projection information. Now here we read the product using that function. I didn't run that cell. Now it has read it using that product directory and product title. Right? So now we will visualize it, but one thing to also be careful here is that in the color map table, the no data pixels are marked as transparent. But because of this notebook, the background of the notebook is white, and also the snow color is white. in the product. If we visualize it that way, it will show no data as white, and we cannot separate those. So what we do here is we add pink color that to be used with no data pixels. Then we use these two parameters to make the plots a bit bigger. Now we can draw it using Matplotlib. So now we see the GF layer, which changes from black to white with blue colors, showing the fractional snow cover. And then the clouds are gray, and no data is pink. Okay. Now we have explained that the product has 7 days of data, and the list of that products and also their metadata is included in the metadata, the XML metadata of the product. Now we can read that XML file, and using that fields here, we can list the products that are used. It is quite useful to see the coverage of the product and what it is formed of. So we can see that it has used many of those, and there is FSC product for the same day, one of them, and there's multiple products that are 2 days old, 3 days old, 4 days, and 5 days old. Now, now we can create, using the acquisition time layer, we can create an age raster to use that for the filtering. Why do we create an age raster? Is that the acquisition time layer in the product, as it is explained in the Predict user manual, it is not directly giving the age, but it is giving the sensing time of that pixel. And it is encoded as the seconds from Unix time. So it's a double integer. Now we need to convert it to age. And for that, we can use a timestamp for the what we call product midnight timestamp, so that it is the midnight, like 0000 at the end of the day, so that the age of, for example, the product in the same day is like 13 hours. We use that timestamp, and we subtract the acquisition time layer. Then we divide it into the seconds in day, so we can have the age in days as a decimal. Right. So another important thing here is that if there's no data in the product, which generally there is at least 1 pixel, so the AT layer is then 0. But for visualization purposes, that's a bit of a problem, because when you have like 0 and higher numbers in a raster, you can have the colors not good for visualizing. So what we can do is we can change it to not a number, none, so that it is not plotted. Now, if we visualize that age layer, we can see the age of the different pixels, right, in days. So this is changing from 1 to 6 days. And we can see here that the more the bluish, it's newer data, and more the pinkish, it's older data. Now we can use that raster to filter the age of pixels. What we will do here, we will create a copy of the GF layer and filter it where the age is bigger than 4, right? So we take the pixels out and we replace it with no data value. Then after doing that, we visualize them together. So this is the original GF layer. And then there's a 4 days mask, which is a binary mask taken from the age layer. And when we mask out the pixels that are older, then they are no data now, so they are shown as pink. All right. So we can change the number here either according to days or seconds or whatever, and use only the data as new as we want. We can do the same with QC flags layer. QC flags layer have different flags for the quality control, and one of that is the sensor type. When we are doing the merging, we are also storing what kind of data is used. So from the, again, the user manual, the bit 6 here is the sensor, the sensor type. So it's 0, it's optical, it's coming from Sentinel-2. It's 1, it's coming from Sentinel-1. And QC-Flex layer is encoded as bitwise. So it's an integer, but in each bit there is different data, and we will use only bit 6. Now we can create a function to read that bit only, because we cannot directly use the integer value, and we can actually visualize QC-Flex. So you see here that that's because of the bitwise merging, it doesn't actually make sense. We cannot get any information like this. We need to read it bit by bit. So using that function, we can read any bit. And if we use that for all the bits, now we have separated that raster into 6 bits. And what are these bits mean? It's in the user manual, but what we are interested in now is bit 6. So we can see here that white ones, which are 1, are the radar, and the other ones are coming from the optical sensor. Now we can create the rasters using the same logic that we used for the age. And since these are already now binary masks, we can use them directly and replace the pixels that we don't want by no data. Now, if we use the same matplotlib script to draw them together, now we see that now we are using all 7 days of data, but we are separating them according to optical and radar. So if we don't want to use Sentinel-1, if we find it irrelevant somehow to our study or applications, we can filter it out, and vice versa. We are quite ahead of schedule, so there's also one last example that is merging those, but I think it's pretty much same, and I will leave it to you as to go over it when you try to run this notebook. Yeah, we will finish this notebook here.
Thank you very much, Jamal, and apologies to everyone that we went over time. It always takes a bit longer, especially with demonstrations, but hopefully you find it useful.